All right. Thank you, everyone. Good morning. I'm happy today to get to present some preliminary results from this past summer's campaign. This is intended to share some early findings with the community as we prepare for summer 2023 with several ground and airborne campaigns in the region. So with that in mind, I'm going to give a brief site overview, but focus mostly on preliminary results, looking at emissions, some markers of oxidation processes and products, and then also talk a bit about temperature effects, spanning a wide number of instruments here to hopefully reach everyone and their planning needs for next summer. So there's a number of field sites throughout the region, in addition to the aircraft that Karsten was talking about. The two sites associated with the NYC METS project are on a rooftop at the Advanced Science Research Center in Upper Manhattan, as well as at the Yale Coastal Field Station, where we see onshore flows coming for most of the day, carrying highly oxidized air from over the Long Island Sound with back trajectories that go to New York City or over Long Island. So these sites both see high ozone. In the city now in Manhattan, we even see hourly maxima that reached up to and over 80 ppb. We actually see higher ozone concentrations down at the Connecticut site. There we get over 80 ppb often, and even over 100 ppb with our hourly maxima. Given my 9 minutes today, I'm just going to focus on observations from the New York City site. So I'm not going to go through this list in detail, but just in synopsis, it's a rooftop site that's located at 90 meters above sea level with a 4-meter tower on top of that. This past summer, measurements were focused in July and into August. Exact dates are to be determined, but will fall in a July-August period of next summer. There were a lot of fantastic people making measurements at that site. This is just a selection of ones from our project, and some of which I'll be talking about today. So you can see a very nice view here of the Manhattan skyline in the photo on the bottom left, and this gives us exposure to a densely populated area of Upper Manhattan. And so one interesting thing here is that when we compare the wind roses across the city, the Manhattan site sees much more influence from densely populated areas of New Jersey, as well as, unsurprisingly, Midtown and downtown Manhattan. But if we go out to Long Island into the boroughs of Queens and Brooklyn, we see much more prevailing southerly flows coming onshore from the Atlantic to the south, with a peak that occurs in the late afternoon in terms of wind speed. So this affects our back trajectories locally within the city and the exposure we're going to see to various sources as they flow to these different sites. The Manhattan site is a very interesting location because it's in a densely populated area, and it also has a wide diversity of sources. There's a lot of high time resolution spikes in this data. The wind direction as it rotates around through the prominent wind directions, either from the east all the way to the southwest, brings inflow that changes the distribution of sources we're exposed to at the site. There's a lot of great work that's been done at this site, including by Rashin Kamane and John Mack in the past. And some of the VOC work we've been doing there over the past couple of years include a paper from Piyush Khare that was recently published and looking at oxygenates, including acetates, acrylates, glycols, and glycol ethers at the site, and comparing them to emission inventories in the winter. And I also encourage you to check out Song Kao's poster. It's online, but he'll be giving a summary tomorrow on Wednesday. And it's also up as an iPoster. And he looks at the importance of wind direction and temperature and other factors of meteorology that affects the site. And so this gives us a lot of opportunities to look at shifting distributions of sources as well as back trajectories and transport to this site with wind direction here when we're in the thick of it all. So just from last summer, I'm showing a D5 siloxane diurnal profile with a spike going up with the morning commute going into midday. And for comparison, I've put the carbon monoxide diurnal profile. It shows a distinctly different shape. In addition to all the VOCs and OVOCs that we observed at the site, we also see a range of intermediate and semi-volatile compounds with offline, as well as some of our online measurements, as TAQ will show in the talk after this. And, there's your classics of your acyclic alkanes or cyclic alkanes and your range of aromatics. But what I've decided to show you here is some preliminary results of a non-targeted search of all the functionalized organic compounds that are including oxygen, nitrogen, and sulfur compounds in the mix. And so we see a range of these functionalized intermediate and semi-volatile compounds, including a fair bit of nitrogen and reduced nitrogen that's present in the mix. And we can zoom in on any of these in a more targeted way. So here just is an example for compounds containing one oxygen atom as a function of compound class. And so we can see a range of acyclic through multicyclic aromatic species. And so just scratching the surface here with a lot more to be done, but there is really an important role here for a wide range of intermediate and semi-volatile compounds at the site, and some interesting variations with particular day samples and day or night samples. So we are amongst a lot of sources, but that doesn't mean we can't pick out some markers of the oxidation of these anthropogenic emissions. And so showing a classic ratio of the C9 aromatics to benzene here on the left, and you can see a relatively stable average benzene diurnal profile below it. But we do see a dip in midday going into the afternoon in this C9 to benzene ratio, showing that we are seeing some oxidation of local or semi-local emissions of aromatics as they arrive to the site, even though we have a high density of sources within about 10 kilometers of the site. For comparison, on the right, I'm showing an ion that includes methacrylin and MVK as markers of isoprene oxidation. And we can see an increase here around 9 a.m. Local time and going through the afternoon. And this could be locally emitted biogenics that are oxidizing on their way to the site, or transported oxidation products. And also there's opportunities for emissions of other compounds in the city that are going to appear on this mass. So with the remainder of my time, though, I want to shift to talk about the aerosol observations. And so these are being led by Tori Haas-Mitchell, and I encourage you to check out her poster tomorrow afternoon. And she's been using measurements from our Queens College Ascent site, as well as the Manhattan site, to look at the shifting composition of aerosols in New York City in comparison to prior AMS studies in 2001 and 2009. And you can see we go from being about half organic to predominantly organic over these 2 decades. This has been driven by reductions in the sulfate and ammonium components, while there's been relatively minor reductions in the organic aerosols. So further reductions in PM2.5, and certainly the emphasis of our studies next summer, need to require a greater focus on the primary organic aerosol emissions from a range of primary sources, as well as emissions and oxidation of secondary precursors from both biogenic and anthropogenic sources occurring in and near the city and from further upwind. These concentrations of organic aerosol display distinct temperature dependence, though. So we see about a 5 microgram per cubic meter enhancement across the temperatures observed at the site. It got pretty hot there in the summer, so anyone who's coming out to the New York region, make sure your instruments are ready to handle some heat and shed some heat. But this organic aerosol temperature dependence shows something similar to what's been seen in the Los Angeles region in the Nussbaumer and Cohen papers and Pennington paper, where we see a organic aerosol temperature dependence in the South Coast Air Basin. By comparison, at the Manhattan site, we see minimal influence from ambient temperature on the black carbon concentrations. If we look at this in terms of the diurnal profile, we do see a slight relative increase in the organic aerosol concentration in midday and through the afternoon relative to the black carbon. And Tori is continuing to dive further into this with her analysis of this data from both sites. So with that, I just want to put up a summary here of some of the points, just a selection that have been brought up today, and I look forward to further discussions while at the meeting or after. And any questions, you can feel free to email me, and I encourage you to check out the various posters that are summarized at the bottom here. So thank you.
we have time for a question? Yeah, I can ask one. I'm just curious, why do you think that the diurnal trend of organic aerosol is different between New York and California? Like for California, there's an afternoon peak, but here it's most flat.
Yeah, that's a great question. And so I put up the meteorology slide early on so that we can think about how that changes between some of our canonical studies we've been doing from CalNex. And so Pasadena sees that arrival of the late afternoon plume coming from downtown Los Angeles and other parts of the most densely populated areas of LA that bring in that afternoon plume that brings with it a lot of less oxidized organic aerosol. And so here we're in the mix more with it. And also we don't have the same exact wind pattern that happens repeatably every day.
Makes sense. Okay, thank you.
Thank you.
Our next speaker, and I will not pronounce it correctly,
It's
Huge. Yeah, thank you. Well, and he's going to be talking about ion mobility spectrometry with ammonium iodide chemical ionization for instantaneous isomer resolved amine measurements, a New York City study.
Okay, thank you for the introduction. Yes, today my presentation will be about in situ measurements of SVOCs and VOCs using ammonium focus that is coupled with ion mobility spectrometry. So in the US urban areas, the fraction of VOC and SVOC emissions from non-traditional sources such as volatile chemical products now substituting that of the traditional sources after decades of successful control policies. And the VOCs, SVOCs from the VCP-related sources are recognized as the key contributors to ozone and SOE formation, as you can see from the bottom figures from the Los Angeles case studies. That is which the products and the process-related sources are marked as in green. That can be referred to some of the non-traditional sources. And then that could be related to the high VOC reactivity of such VCPs on the right pie chart. And still, there are large uncertainties remaining regarding the relative contributions of various sources and compound classes to the urban reactivity and the secondary pollutant formations. And for such from the non-traditional VOCs, the formulation of VCPs includes some large fractions of oxygenated VOCs and SVOCs, which now I'm going to just refer to OVOCs. And the large urban fluxes of OVOCs in the VOCs has been kind of observed with the limited speciations. And this ambient composition of such OVOCs can and contributions from some of the sources remains uncertain in the emission inventories, which can be shown in the right figures here as an example from a case study from the New York cities during from one of our group, showing that the comparison between the observations versus the VCP models having some differences, especially for some of the OVOCs here. And some of these uncertainties can come from the formulas here can have some of the multiple isomers with different structures. And this could affect some of the secondary chemistry in the urban atmosphere. And so the experiments are performed at the New York City sites during 2022 summer for all the detailed description of this field campaign has been kind of shown from the previous talks by Professor Drew Gantner. So the 4-meter tower is set up on the rooftop with having a gas sampling inlet using the half-inch PFA tubing that is shared by the Vocus IMS and Vocus PPR that is using the hydrogen ions as the reagent ion, and then Tildes and some of the offline sampling using the gas absorbent tubings. And we set it up with the high flow rate setting up around like 50 liters per minute to minimize some of the VOC and SVOC losses. And we zeroed the inlets twice each hour to measure some of the backgrounds of the instruments. And today's presentation, I'm going to mainly focus on the Vocus IMS using the ammonium reagent ions. So the reason why we use the ammonium reagent is that it is reported to selectively ionize some of the functionalized species that has been difficult to measure using the hydronium ion due to some fragmentations and low proton affinities. As you can see from the left figure, where the ammonium 12 is measuring having some of the better sensitivity across the broader mass to charge ratio range compared to the hydronium ion. And the chemistry of the ammonium or ammonia gas reacting with VOCs can be summarized in the equations on the top. And we expect most of the VOCs to detect it in the instrument as in the ammonium adduct to the VOCs. So the focus here, we injected ammonia gas injected into the focusing ion molecular reactor, which and then it is coupled to the the ion mobility spectrometry using the SLIM technology, which stands for the structures for ion manipulation, structures for lossless ion manipulations. And we use the helium as in the buffer gas. So once the focus, the gas is sampled through the focus, it travels through the ion mobility regions, and then it reaches to the top MS where we actually measure each compounds. So for the SLIM IMS technology, the SLIM takes a long path length and puts it into a compact space using PCB technologies. So the ions, once it is sampled when it reaches to the SLIM regions, it's going to travel through this PCB parts following the arrows here. And this traveling wave drives the ions along the PCB surfaces by taking the different voltage in an electron rod in between the two layers of the PCBs here. So depending on the ion size, the larger ion is gonna travel a little bit, reach the mass spectrometry later than the smaller ion molecules. And this is the one representation case of how the focus IMS data looks like. As in the 2D diagram here shows that y-axis is the IMS drift time, as in the milliseconds, and the x-axis is the mass to charge ratio that is color coded by the ion abundances. And if we take a more close look into one of the masses, as an example of here for the M2Z 116, as an example, 6H10O, can have is showing some of the the IMS drift peak, which might indicate that the presence of multiple isomers is existing at this particular masses. So we're gonna kind of more dive into some of the example data during the field campaign, and we chose the July 22nd based on the ACSM organic measurements and the VOC measurements using the Focus PTR. And then so the details of this, So the details of the results here is shown will be more. You can check it out in the poster by one of our group member, Tori Hass-Mitchell, later. And then we chose the July 22nd as during some of the high OA period for the preliminary analysis here, as with a mix of like primary emissions and the secondary oxidation products. And the VOC concentration that I shown here is mainly from. We preliminarily selected the ones from the C8 and C9 aromatic compounds. So here are some of the compounds we chose as a representative case based on one of the previous studies that it was held in the same locations using the ammonium focuses that has the high emission ratios. And some of the label compounds here are determined based on the standard injections at the end of the field campaign. And the many of VOCs here seems to have some single isomer dominated by the single isomers, but some of the compounds such as like C5H10O2 or C4H6O2 and C5H8O2 may are having some different multiple peak patterns, which may indicate that these specific formulas may have different isomer distributed throughout the field campaign. And some of the interesting things that we also found is that some of the compounds are identified to have the diurnal patterns. And so here the red marker plot shows the results from the morning. And the black here is the one that we acquired during the evening. And some of those compounds so far we haven't identified that has some clear diurnal patterns are mainly C5 or C10 compounds that could be related to the secondary oxidation products from the isoprenes or monoterpenes. And among all these compounds, especially we find that C10H16O2 has the most clear diurnal pattern with high peaks of the IMS drift time during the morning, while the first peak that appears in the IMS drift is significantly decreased at the evening. We also observe some of the compounds having different day-to-day differences in the isomer distributions, and especially so far we find that this was observed in case of some of the phenols or cresol-related compounds. So, for example, of C7H8O or C8H10O, they do have some single isomer dominant during the July 22nd, which is marked as in colored in red. But if you look into the bottom figures, where we also include the July 20th data, they have the multiple peak patterns, which may indicate that some of the days they might be dominated by some single type of the isomers, while the other days it could have some different types of isomers for this common compounds. And for the C6H6O here, where it has the peak, it's kind of shifted from around 40 millisec to around 42 or 43 milliseconds from July 22nd to July 20th. So in summary, using like ammonia reagent chemical ionization enables us to measure some of the compounds that has been challenging to measure. And deploying the Vocus IMS made it distinguish some of the oxygenated VOC and SVOC's isomers at really high time resolutions. For us, we kind of set it up around 5 Hz during the field campaign. And then, so we could have both high resolution data as in terms of chemically, and also as in the temporally. So some of the observations here includes the primary emissions and the secondary oxidation products having isomer distributions that has differed diurnally, and then it could have some different isomer distribution across the field campaigns. And so this is all my today's presentations, and thank you for your attentions.
There's a quick question. If not, given the interest of time, we're going to move on to the next topic.
So our next speaker is Yuying Liu, and the talk will be about investigating impacts of local circulation on coastal ozone problem in New York metropolitan area.
Thank you. Thank you. I'm Huiying Luo from University at Albany. So today I'm going to talk about the impact of local circulation on coastal ozone problem in the region. So elevated surface ozone is often detected in the region during summertime due to the local, the high rich sources of local anthropogenic and natural ozone precursor emissions. And because of the intricate and complex boundary layer circulations induced by this complex geometry as shown in the map, there is often observed sharp horizontal and vertical gradients and distinctive diurnal cycles under the influence of complex boundary layer circulations. And the impact of the circulations is studied across the world in the coastal regions. And there are two major methodologies. The first one would be compare the cluster-based local circulations conditions and also maybe sea breeze and non-sea breeze days. And the second one would be using the observation or numerical modeling-based case studies to explain the process. And in this study, we will first introduce the impact of temperature into the discussion and examine how the spatial and temporal or ozone characteristics under different cluster-based circulation scenarios, as well as temperature levels during the summertime of 2017 to 2019. And also we examined two representative case studies during listos to study the critical background wind conditions and sea breeze features that help moderate the ozone exceedances during extreme high heat. So the study begins with the cluster of the wind conditions and temperature profiles in the region, and we pick the Queen's College site to do this analysis. The wind is clustered based on normalized features listed here, adapted from LEED 2020, and the green 2 features are adapted for the region specifically to make to distinguish between the sea breeze days and the southerly days, which both tend to have the wind from the south, but different diurnal features and magnitude. So here are the 4 time series of wind conditions. And we have the westerlies, southerlies, oscillations, and sea breeze days. And looking at the wind roses, we see like there is a relatively clean cut among the clusters. And the temperature is also clustered based on the K-means, and based on K-means using features from hourly mean temperature. And the results are 3 categories: hot, moderate, or cool days. And we first look at the all-weather ozone distributions of the daily maximum 8-hour ozone during the 3 summertime. So for the maps here, the first row shows hot days, moderate days, and cool days to the last. From left to right is sea breeze, oscillation, southerly, and westerly days. And from this, we see like the first thing we see is that the temperature and local circulation have distinctive impact on ozone levels. And secondly, take the westerly days on the last row as example. We see that like the high ozone levels tends to happen in the south of this dashed black line, and we conclude that different wind patterns have similar impact on ozone spatial distribution at all temperature levels. And lastly, we see like the highest ozone is closely associated with the hot sea breeze days, which is on the top left, followed by the hot westerly days. And moving forward, we are only focusing on hot days where high ozone tends to happen. And looking further, we see that actually during hot westerly days, there are 2 different wind scenarios based on the south of Long Island, where we have the westerly sea breeze days, where sea breeze days actually developed in the south shore of Long Island, but it's delayed and its penetration into New York City and southwest shore of Long Island Sound is intercepted by the dominant westerlies, and also the westerly days, where the westerly is very strong and there is no sea breeze developed in the region. And it's removed from our analysis on the hot days, since the ozone tends to be very low and number of days is low. So by excluding those westerly days, we see like the ozone on the westerly days actually increased a bit, but still the percentage of the ozone exceeding the national standard of 70 ppb is decreased, while a dramatic decrease in the westerly sea breeze days as southerly days compared to the sea breeze days, where in the sea breeze days in New York City and South Shore of Connecticut, there are half of the days that actually with very high ozone exceeding the 70 ppb. So looking at the reasons here, when we compare the daily maximum 8-hour ozone, the sea breeze and the westerly sea breeze days, we see like there is a dramatic drop of 10 to 9 ppb during westerly sea breeze days, and for the Long Island region, in the meantime, there is the ozone level is comparable because of the sea breeze and the westerly front in the Long Island Sound, south shore of Long Island, as indicated by this dashed line. And lastly, we look at the southerly days where it's represented by the black line. We see like lowest ozone levels are observed during these days because of the presence of the relatively clean marine air. And it's reflected by the moderate diurnal variations in the temperature. And moving forward, we'll only look at the hot sea breeze days where ozone level is the highest, and also the regions of New York City and South Shore of Connecticut. And to study the impact how meteorologic conditions modulate high ozone levels, we exclude those days that it has a relatively lower temperature to exclude the impact of temperature. And the features we studied are the sea breeze features observed at Wonton listed here, and also like the sea breeze arrive time at the ozone monitoring sites, as well as the regional meteorologic conditions such as wind conditions and daytime mean temperature. And among these features listed here, we found that the most different features that can help moderate ozone exceedance or non-exceedance is the transport features, which is related to the background wind conditions in the morning, and also sea breeze features such as the instant change in wave wind component when the sea breeze onset and the stress of the sea breeze. And each feature will be illustrated using the following two examples. So the first example is a gradual weak sea breeze onset on August 29th and 28th. So the Wonton side, the black line shows the gradual increase of the wind component, and also because of the stress morning southerly wind, the stress of the wind, the sea breeze is relatively low. And we see on this kind of days, ozone in New York City is lower, rather while the ozone time series on the right side at Westport, which representing the connected shoreline, is high. And during some of other examples, the increase of the hourly increase in the ozone on Westport can be as high as 40 ppb. And looking into the region, we see at 4 different times throughout the day, we see like high ozone presents in the South Shore of Connecticut rather than New York City, where the ozone is relatively low. And the green shade represents the rough estimate of sea breeze front location based on her products. And looking at the reasons, we see that the distribution of NO2 tends to have a much large impact because of the relatively concentrated emission. And during these kind of days, both regions have NO2 saturated, so we have higher ozone levels in the both the regions. While the other case we have look at is the abrupt strong sea breeze onset, and it's reflected in the time series of wind component at Wonton, which is the black on the left, where we have like the abrupt sea breeze onset. And in this kind of days, we see like the ozone in the Westport, which is in the right figure, plateaus at early hour around 10 a.m. And looking into the region, we see in this kind of days, high ozone is concentrated in the urban center, while the connected shoreline has a much lower ozone levels, which is also can be explained by the NO2 in the region. The NO2 is diluted a little bit, concentrated around the city center and recirculate back in the early afternoon by the sea breeze onset. So to quickly summarize what we learned from this observation-based study, we see the most polluted days are associated hot sea breeze days, and also different wind patterns have very similar impact on ozone distribution at all time on temperature levels. And the westerly days, westerly sea breeze days has much lower ozone level with by dropping from about around 9 to 10 ppb compared to the sea breeze days, and the probability of exceeding the national standards is also dramatically decreased. And the two conditions with when high ozone, extreme hot sea breeze days with actually daytime with average daytime higher than 29 Celsius in the region, when a relatively stronger southerly wind component in the early morning will likely to lead to abrupt sea breeze onset and contribute to a lower possibility of ozone exceedance in the South Shore of Connecticut. On the contrary, when a relatively stronger southerly wind component in the morning will favor a gradual weak sea breeze development and typically yield a lower chance of ozone exceedances in the urban center. So thank you so much for your time and attention.
Limited by time, we have to move to the next topic. Thank you.
Thank you.
Our next speaker is Alexandra Carabelas. She's going to talk about modeling the impact of local and regional emission sectors on ground level ozone formation in and downwind of New York during listas.
How do I click? Cool. Okay. Hi, everyone. I'm Alex Carambellis. I am an environmental analyst and photochemical modeler at the Northeast States for Coordinated Air Use Management. And today, thank you for the introduction. I will be presenting some sensitivity analyses that I've conducted with the WRF-CMAQ coupled model. A quick shout out to my collaborators on this project. Without them, we wouldn't have had the idea for it or some of the input data. So I really appreciate everyone's involvement. A little bit about the motivation behind this work. So it stemmed from the 2018 Long Island Sound tropospheric ozone study. And that study was a large endeavor to better understand the consistently elevated ozone pollution problem in New York City and coastal Connecticut. Some of the work that came out of that is shown in some of the analysis that came out of that is shown in the bottom right-hand corner, courtesy of our collaborators at Columbia and MIT, evaluating an ozone regime shift between non-exceedance days and exceedance days using GCAS Geotazo and TROPOME data during the Listos field campaign. So from a regulatory perspective, states and cities are interested in understanding the ozone regime in their area in order to develop effective policies. And so this got us thinking about how different source categories that are major, such as on-road sources, or smaller, such as high energy demand day peaking electricity generating units, might impact ozone concentrations in the region, specifically in applying these together and seeing what happens to the ozone regime in the region and downwind, and then layering on the different source sectors to see what happens. Okay, so this led us to design a project around these policy relevant research questions. Specifically, how do NOx and VOC emissions play a role in ozone formation and concentrations in the New York City area, coastal Connecticut, and the Long Island Sound? And to what extent do NOx emission inventories and scaling choices impact the perceived effectiveness of different ozone control strategies? So thinking about if we're in a completely different ozone regime, how can a smaller emissions modification make a difference as opposed to what it is at present? Just a brief review of our modeling tools. We used the coupled WRF-CMAQ model at a 1.33 kilometer resolution. Basically, it stretches from the southern tip of New Jersey up through covering Connecticut. We have inputs from our EPA collaborators that include meteorology, emissions, initial and boundary conditions. The emissions were updated to 2018 using 2016 and 2017 inventories and some 2018 base data. and those are detailed in the table on the right-hand side. We have data for the entire summer season from May 15th through the end of September of 2018, discarding the first half of May as spin up. But for this project, we focused on sensitivity time periods of July and August of 2018. So that's what I'll be showing today. Just a brief overview of our sensitivity modeling design. We combined a 90% reduced on-road emission scenario where we just cut 90% of all on-road emissions across the entire domain. So no geographical masking or anything, just that entire domain on the right-hand side. And we applied some high energy demand day modified sensitivity scenarios that were previously developed through work that I collaborated on with the Ozone Transport Commission. These were NOx only modifications, and the scenario that I'm showing today prioritizes the lowest emitting high energy demand day units. There are additional sensitivity simulations that we conducted, including zeroing them out entirely, prioritizing based off of the highest emitting units, and prioritizing based off of what is typically used. But today we're showing just that combination of the on-road reduction and prioritizing the lowest emitting HEDD units. So now getting into some of our results. Here, what I'm showing in the top 4 panels are the average concentrations when ozone exceeds 70 parts per billion in the baseline scenario. So you'll see that going from left to right, the average concentrations across the domain do decline, and that's because there are lower concentrations on the baseline days that originally exceeded 70 parts per billion. So moving across, we see that in the baseline compared to the HEDD sensitivity only scenario, there's not really a significant change, maybe an average drop of about half a part per billion, max part per billion. Ozone concentration drops again about half a part per billion. When we transition into that on-road reduction, again, cutting 90% across the board, we see a much more dramatic improvement where the average ozone concentration on these high days drops from about 78 to about 70. But then we see that there's a pretty minor change once we start layering in those HEDD unit modifications. So again, we're prioritizing the lowest emitting units. So overall, there is a reduction in the localized emissions from these units in the region. And we can see what those differences look like on the bottom panels. So we see in the baseline at present conditions that there are some pretty strong localized impacts from modifying those HEDD units. Plugging in just the on-road emissions reductions, we see a very widespread reduction of up to 21 part per billion in ozone concentrations. And then those white grid cells, those are water bodies. And then finally, in that far right bottom panel, once we layer on-road reduction and HEDD units, we see that those impacts as a result of the HEDD units is much more muted than in that baseline comparison. And we see that this occurs because by reducing our on-road emissions to such a dramatic extent, we have a ozone regime shift. So this is following up on some of those plots that I showed at the beginning of the presentation from following work from our collaborators at Columbia and MIT, showing the formaldehyde to NOx ratio in the baseline for certain exceedance days on the left, the category or the simulation with our lowest emitting HEDD units in the middle, and the 90% reduced on-road simulation on the right. They're the same. One is just more, the top and bottom are the same. They're just more zoomed in on the top. And so what we can see is that in the baseline, and then just by applying the lowest emitting HEDD units, there's really not much of a shift. That same NOx saturated regime in the blue still exists for the most part between those two scenarios. But once we reduce emissions pretty dramatically, we see that there is no longer a widespread NOx saturated environment on these ozone exceedance days. And instead, there's kind of this broader transition both to a transitional and a NOx limited regime as defined for the New York City region. We can see how this regime shift applies to concentrations at our specific monitor locations. And so here we've selected a VOC sensitive, a transitional, and a NOx sensitive representative monitor. Those blue bars are showing the impact of HEDD units in kind of the baseline scenario. The orange lines are showing the impact of the HEDD units after that transition after that regime shift as a result of the reduction in on-road emissions. So generally what we see is that there's this shift overall at these monitoring sites, even central to New York City, from VOC sensitive to NOx sensitive within these blue to orange bars, with a few exceptions. So just kind of walking through, generally we see that they're in these VOC sensitive regions in the blue bars, there tend to be some more disbenefits to prioritizing lowest emitting HEDD units, which is that lower or that smaller emission source category. We see that both in the VOC sensitive and in that transitional represented monitor. But when we plug in that large reduction in emissions, we see that there are fewer disbenefits and greater benefits that are highly localized at these monitors as a result of this additional introduction of emissions reductions. So just to kind of summarize, what we were able to determine was that there are differences in how these smaller source categories can impact our model domain, whether it's in the baseline or in the high, this regime shifted low on-road emissions environment. And so what that says to us is that as we continue to make these transitions to more NOx sensitive environments, we recognize that these smaller units or these smaller source categories might have a larger impact on overall concentrations. And so just really quickly, before in my 16 seconds, I'd like to acknowledge NYSERDA for funding and the Connecticut DEEP Department for supporting our computational resources.
We have time for a very brief question, if there are any. If not, we'd like to move on to the next presentation.
Thank you.
Our next speaker is Guillaume Gronov, and the talk is Observation of Pollution Events at Low Altitude During Tracer AGU, the Advantage of Adaptive Resolution LiDAR.
Hello, thank you very much for having me. I am Guillaume Gronov from NASA Langley. Okay. Okay. So first of all, I want to thank all my co-authors for this work. And what I will present you today is something that is actually frightening a lot of modeler, better data. So let's start by understanding where we took this data and how we did that. So it was during the Tracer AGU campaign. So it's a little bit after the Listos campaign that we spoke before. Tracer AGU happened last year, 2021, in the Houston region, and we had several instrumentation, including LiDARs over there. The objective was to better understand the ozone photochemistry and the meteorology in that environment that is quite complex, to be honest, because there's a lot of source of pollution and a lot of traffic and other things that are problematic for modeling and for observation. Our work over there with LiDAR, with the Tornado LiDAR, was to support the ozone observation by providing vertical profiles and long duration observation. Our LiDAR, the Langley Mobile Ozone LiDAR, LMOL, was located at the University of Houston, and it was near a couple of ground-based instruments, including some Pandora and some ozone, SO2, and NO2 monitor. It was also supported by UAV and by ozone sondes. So very quickly, Houston, that's where we were. And for those who do not know really the LiDAR, it's a part of the Tornet network. So it's a system that allows to assure the quality of the data. It forces some parameters and some uncertainty validation that allow us to have something that has proven record for the data. So when I am showing you some data, it went through some validation first, and it's difficult to be able to say this is poor data from the on-go. We need to discuss it. And I say that because there's some surprising results. So NMOL has some unique capabilities because all the LiDAR are not with the same system. We are able to have more or less power. So our LiDAR is able to have a resolution, vertical resolution between a few dozens of meters to a kilometer, and temporarily it's a 5-minute resolution. And we are able to go from 100 meters to 5 to 7 kilometer altitude during the day in function of the condition, and more than 10 kilometer altitude during the night. During the campaign, we had 228 hours of operation, and they are available on the NASA Langley website. You need just to search for Tornet or to search for the tracer AGU. So the case that is interesting us today is a case of September 9th. So this is a very crude analysis of our data for that day, where we forced a 500-meter resolution for the LiDAR. And what I'm going to ask you is to look at that part here. And with that resolution, it looks like there is basically nothing here. We see some very large gradient between the ground-based observation, the blue line here, which corresponds to very low ozone, and the red, which corresponds to 80, 90 ppb of ozone. We have this big gradient in the morning, and it starts to get normal in the afternoon. And you see that there is some plumes here that are staying from earlier during for the previous days. But that's 500-meter resolution, and we don't really know what is happening here, and it's quite problematic. So with our system, we're able to increase the resolution, and it's totally something that is done by doing some analysis. It's changing the analysis, not changing the data. And what you can see is that in the first 100 of meter, you have a huge ozone layer. You see, that's the same data. But we see by increasing the resolution that we have actually a higher gradient than what we were expecting from the other data for that day. Problem is that when you do that, you are losing all the data at a higher altitude. So one would say, instead of having 125 and 500 resolution, why don't you take just 250? And it's that. It gives us a little bit of everything, but it's still a poor compromise with respect to what you want to analyze in this data. So we have something better for that. We have what we call the adaptive resolution system. And it's based on, instead of trying to keep a resolution, you try to keep the signal to noise ratio in function of the altitude. So it needs a lot more computation, but you see that you have a better picture of what is happening during that day with that low layer here, that other layer, the one from the day before, and all this very important gradient at the bottom. As a comparison, when I did that vertical resolution, I was able to compute what was the actual resolution, and we are able to see here that we go from a few dozen meters to up to a kilometer at high altitude. And that weird change here, it's because we have two channels on our LiDAR. So we have one channel that gives some data and then the other one. And that's what allows us to be through that range. So from there, we have quite good comparison with the ozone zones. Actually, it's very hard to have such a good comparison when we are here because we have a huge gradient. And the thing that with such data that looks that weird, is there a model that is able to support our observation? And yes, there is a model. And it shows some huge gradient near the ground. So you see that's basically for the same hours here. You see at low altitude a very low value of ozone and higher values of ozone over here, but it's not going up to the huge ozone values that we're actually observing here. And there's a lot of question about that, but maybe first we should look at other species such as the CO here, SO2. SO2 is a very well-known species that affect the ozone data from LiDAR when we take poorly into consideration the wavelengths. The thing is that we took the wavelengths for our observation into consideration to have no impact from SO2. So it's not affecting us. So to better understand that, we looked at other days and we saw that there is this day, the 27th of September, where we actually saw that gradient at low altitude and we saw it increasing and we had even a little ozone zone. And what it shows is that we have traffic and industrial plumes that are coming, that are affecting the ozone close to the ground. We have titration events. So here, that's one of the example of this titration event, where you have ozone in blue, and you have coming of NO in red, and NO2 was basically 0, went to the level of ozone where ozone was titrated, and basically showing that it's what is happening here. So very low plume to make the titration, and we still have the high ozone plume at higher altitude. But it's still very difficult to model and to have everything over there. So what this presentation was, I hope, showing you is that when we work with LiDAR, fixed resolution has a strong limitation. And by doing a very good analysis, we're able to highlight all the details and all the dynamic at our location. And well, thanks to a campaign like the Tracer IQ campaign, we are able to do this observation and have a lot of interesting analysis of all these species. Thank you.
Are there any questions?
May I ask one?
Yes.
So for the ground level ozone, you
Yeah.
showed that midday it was at the lowest. Would you expect something like that when for the chemistry is at the highest, that you get low ozone concentrations?
So basically, the low zone is really coming from titration here. In this day that I was showing,
Okay.
we have other days where it's clean. The air is clean because we had rain, and so that's